Okay, guys. So we are in MATLAB coding, but before extending the code and sharing with you tonight, I'm then going to Laplace transform for the first order and second order systems. So I want to make how to make a movie or model physical system in MATLAB. Okay. For those of you that you are in my vibration class, you may know, but for those that you are new, you have to know how to do it. So this was our problem, M and the L and the theta. Yes. Oh, thank you, man. So, what is that? Here we go. Here we go. Can you see it? Yes? Okay. Okay. So, so now, so we had two problems, right? I remember that I did invert. So I did invert pendulum in the class, right? Yes? Did I? Okay. So ML. So I want to make a movie of this in MATLAB because the name of the course is the modeling of physical system. Modeling is not enough these days that you develop what I have done mathematically, solving differential equations. They are good, but if you cannot visualize after graduation to your boss, you are a very weak engineer. See what I'm saying? So simulation and modeling is very important step. Okay, so in MATLAB, if you want to make a movie, first, forget about everything. Let's focus on this line because I want to make a movie of how it moves. Okay, this line. So I'm gonna say the MATLAB plot. I'm gonna exactly use in MATLAB. So I'm saying that because this is fixed, the coordinate of the system I'm going is 0 and 0. I mean that because you remember it was our coordinate system x and y. Yes or no? Okay. So I'm gonna say 0 and putting this and 0. This is x. Oh, I'm sorry. And now position of this. Oh my God. Position of this point because you have two lines. See, two lines. I mean one line. This point. So position of this point with respect to the origin is how much? Is x is L sine theta. So you write here L sine, star means multiplying method, that's right. So this is x component of this line. Then you put colon. Now y of that. Y of this point is 0. And the y of this point is how much? Guys, how much is this? L cosine theta. But negative. Why? Because it's under the datum. See what I'm saying? Okay, hold on, guys. Hold on. Oops. So, oh, what is that? Okay. So, and the y of this point is minus oh my God, minus L cosine theta. Okay? Clear, guys? Clear, everybody? So this is x component. This is y component of that. Okay? I'm receiving many calls. I don't know why. I'm sorry, I have to, I don't know what you have to do. Okay, so we plot the line. Okay, now when I want to try to do this in the code, I'm gonna put the same plot x of this point 0, x of this point gonna be again L sine theta, y of this point and y of this point, but plus, because this is about that here, L cosine theta. Understood? Yes? Now, if I want to plot this circle at the end, you know that the equation of the circle is, we write as this, x of this circle is x of its center plus, okay, x of plus r radius of this circle cosine, say gamma. Gamma is between 0, say to 0.1 to 2 pi. It means starting from this point, 2 pi. See, 2 pi. 60 degree. Yes. So this how to plot this, circle at the end. X of z, let me show you. X of z is how much? X of the, yeah, x of z is the x coordinate of the center of the circle. Here it is. That's right, respect to the coordinate system. Is L sine theta. This is x of z. Center of the circle is x component. X component. See what I'm saying? And now, if you want to plot the circle by itself in r cosine gamma, and gamma is between 0 and 160. See? This is a circle. Here is 0, but you have to rotate here like this. 360. So y of the circle gonna be yc, y of the circle plus again r cosine gamma. Y of c is how much here? Minus L cosine theta plus r cosine gamma. Clear? Good. Now I'm going to MATLAB. Exactly, I'm going to copy this here and make a movie. Okay? Based on the OD that I developed previously. Until it comes up, I'm going to pause it here. So, this is the code that we developed, remember, from previous class? I'm going to share, after I'm done today, I'm going to share with you. Let me open the proper one. ME430. Here we go. These are the codes. Okay. So, this was pendulum. This was the solver. I'm running again for you. Okay. See that giving the initial conditions, your system oscillates forever because you have a pair of pure imaginary poles or roots. Okay. So now again, I'm putting this 0, the initial condition for the velocity of the pendulum, and this is the initial angle. Okay. Now I'm gonna go and make a movie of this. First, look at here, guys. Pause command. Pause. Okay, see guys, I showed you previously. When I'm solving this, okay, if I want to make a movie of whatever I told, this is the angle at time 0, angle at time 0.01, 0.02, 0.0. I have to plot each one by one. See what I'm saying? Yes? And then put in the for loop. I hope that you learned in ME202 MATLAB coding class. But if you didn't, fine. So first of all, what I'm going to do, I'm going to say size of this vector. Which vector? Size of angle equal to size of this theta 1. Let me show what gives to us. Removing this. The size, this is a command in MATLAB, gives you a size of a vector. A size of a vector. See? Let me delete everything here. Okay. Oh, that's has this capital T. Okay. The size of this vector, we have 1001 vector and that theta. Okay. So by having this, I'm going to develop a code. I'm putting counter, okay? Counter. First element of that and first element of this vector, okay? The first element of that. So I'm going to say to size of theta, but which element first? I'm going to say 2 and 1. Sorry, 1 and 1 means this number. Okay, do you understand what I have done? Yes. First element of this increase to 1 by 1 to read all theta until when? Until this final element of this angle. So now I'm saying figure number 3 because already have 1 and 2. Plot. Here we go. Now plot what? I'm first talking about this 0 L sine theta. Yes? So guys, what is L? I'm backing here. Omega n was 1. All of you go to your notes. I want that you let me know what is omega n, natural frequency of the pendulum. All of you, I taught you. Give me the answer. I know the answer. What is omega n? Omega n is based on gravity and length. Share with me. Is, guys, can you hear me? Guys, hello? Disconnected. Oh, I have to shut it down. Disconnected probably, huh? Guys, you cannot. Guys, can. Oh. I can hear you. Okay. Sorry, I couldn't hear you. So, what is omega n? Sorry. Yes. So, if you want to write in the code, L, length of the pendulum, gonna be G omega n squared. Yes or no? Oh, sorry. G over omega n squared. Yes or no? Okay. So I'm exactly putting here. I'm saying, okay, gravity is 9.81. So length of that equals to G divided by omega n squared. Here we go. Clear, guys? Yes? But we need L. So I'm saying global. This is command in MATLAB I'm teaching you. When you say you make a variable global, it's gonna read everywhere. So I'm saying L. Make global for me. Understand? Yes? Yes. So I'm putting the same here. I'm saying, okay, make global for me. Global L. Now you don't need to define L everywhere. You just put it here. So, okay, now let's go 0 L cosine. Exactly, I'm copying here. See here? Sorry, L sine theta. L sine but theta. So you have to say our angle and radian is this, theta. You have to say theta, but which element? Look at here, guys. This is theta, this. If this means go and read all the rows in the first column. Remember, all the rows, this is all the rows and the first column. Now I'm gonna, but I need first row, first column, second row, first column, third row, first column for this for loop. So I'm gonna say con, okay, inside the for loop, and the first column. Okay, done. See what I have done? Yes? Because when I run this for loop, con gonna be 1 comes here. Theta 1 and 1. The next round con gonna be 2. Theta 2 and 1. 3 and 1. 4 and 1 until 1001 and 1. See what I have done? Yes, everyone? Okay. Now, let's go this. Y. 0 minus L. See, now it can detect the L. See, because I made it global. Cosine theta con and 1. Here we go. Okay. I'm doing this and for now because I just want to see how it looks like. Okay. So let me run it. First debug it and then run it. Here we go. See, a line is moving. But you may tell me what the hell is this because it's not moving. It's joke. Yes, you're right. Because I have to make an axis for this. Okay. How? Please turn off your microphone, okay? Guys, please turn off. You're gonna say axis. I'm gonna put axis between -6 and 6 and 0.5 and -4 and 0.5. This is x, the limit of the x of the axis. This is the limit of y. Okay. Now I'm gonna run it. Oh yeah. Now you see that everything is moving, but I need more space for y. Do you see that? Yes, everybody? And for the x. So let me fix it. -8 and 8 and -6. And I'm gonna make it line width. I'm gonna share the code with you when I'm done. And I say 2. If I run this, I need more x. Because I don't know what is there. 12, 12, 10. Here we go. Do you see? The pendulum oscillating. Do you see that? As we told, sine until the time finishes. Clear? Yes? Good. So, But to make it symmetry, I'm gonna make it this 15 to make it more reasonable. I'm gonna take this one. Okay, now, but I have to plot this this circle here. What I'm gonna do, I'm gonna first define this x of the circle and the y of the circle. So, as I told you, you have to define x of circle. Okay, I'm saying 1 because I'm gonna go to inverted pendulum. Gonna be L, again, sine, exactly this. So L sine plus radius of the circle. I'm defining here. I say radius of the circle outside of this loop, I don't know, is 0.5. Huh? We're gonna examine. RC in, say, gamma. We have to define gamma. Gamma is between 0.01 to 2 pi. Here we go. See what I done? Okay, guys. So, and you can comment your code for not confusing. I'm gonna do that because I'm gonna share with you. This is radius of circle at the end of pendulum. So, and okay. So now we defined x. Now y of the circle, as we did, gonna be exactly this, minus L cosine, because we're gonna do that in every second, plus RC guys, I made a mistake here, guys. Look at here. Okay. If you assume a point on a circle, and here is gamma, so x of c gonna be x of c plus x cosine gamma. Here gonna be how much? How much? Sine gamma. See, here is r. Here is r cosine gamma. Here's gonna be r sine gamma. On the other hand, we are circulating this point like this. See what I'm saying? Here you're gonna be sine. When you teach morning, it's gonna like that. Okay, sine gamma. Please fix this. Okay. So, oh, what happened? Okay, I'm coming here. So it's gonna be r cosine gamma. Cosine gamma, and this is gonna be RC sine gamma. So we define those. Now I'm gonna plot it here. If you want to keep it at the same movie, you have to say to MATLAB, hold on. It's understand. It's a command in MATLAB. Hold on. Okay, hold on. Now I'm gonna say there is a command in MATLAB. Fill means fill the area that you defined. Fill xc1 and yc1. With which color? With the color of red. That's it. Okay, this is a command in MATLAB. Fill the area. Okay, so let me run it and debug it. Here we go, guys. See, it's plotting that the circle. Oh, what you see, guys? We named this stick diagram. You see, it's not moving anymore. It's plotting every second. Why? It has a reason. Because when you define here hold on, MATLAB assume it and never terminate that. So after you are done with everything, you have to say, okay, hold only this on. For the rest, for the next loop, hold off. When you reach here, after you are done, you reach the next loop, hold off. So here we go. Here we go. Did you like it? Yes? Now it's oscillating as it's supposed to be. Clear? Yes? Everybody? Okay. Now, when I share this, please go and work with the code. Now I'm gonna say, you know what? Grid. Okay? It's gridding your movie. You can see what's going on. But when I started the course with you guys, I taught you. Okay, it's recording. I taught you this, guys. The original differential equation for the pendulum that was nonlinear was this. Remember? We linearized and we ended up with this. Yes or no? Yes? Yes, everybody? And here we are modeling this, guys. We are modeling the linearized differential equation. So I want to compare, after linearization on the equilibrium point of the zero, what's the difference between them? See what I'm saying? Around the equilibrium point. So here I'm going to adding two more state variables. Okay. I'm going to now, at the same time, I'm going to model nonlinear with linear. Exactly, I'm copying this here. Look at here. Here we go. Okay. I'm going to say is D3, 4, 4. Here was sine M1. Exactly. See? Yes, everybody? Is sine M1. Look at here. This is sine, only changed here. This is what theta. Sine of theta. Are you following me? Yes? Yes? So I'm gonna add, so 3 and 4 are for what? Are for nonlinear differential equation. I'm gonna put the same initial condition to compare them, their motion. So what I'm gonna do, these are the same for that, okay? Except, now you understand why I'm doing 1. Except here is 2, here is 2 for the nonlinear one. This gonna be 3, this gonna be 3, because the angle of the nonlinear is third state variable, this 1, 2, 3. The velocity of the nonlinear is gonna be 4, okay? And I'm saying these are the same, okay? L sine, L cosine. So I'm gonna add it here. Here we go. This gonna be 3. This gonna be 3. Okay. And hold on. For the nonlinear one, hold on. This gonna be 2. This gonna be 2. So I'm commenting here because I'm gonna share with you. This is for particle for nonlinear differential equation. Okay? I'm gonna change the color of that. So if it was blue by default, I'm gonna say the color of this to distinguish between is green, and I'm gonna make the color of this also green. And let me keep them all blue for the first one, and the second, you know what? I'm gonna change. I changed my mind. Red. Okay, everybody. Now I'm simulating the nonlinear differential equation of the pendulum with linear. Okay, let's see what's the difference. The first, they overlap. Nonlinear is the red one. Linear is the blue one. You see that we linearize differential equation, and they have such a difference. Small, but they have difference. Interesting, right? Is everybody? Yes? Yeah, hold on. Where? This or this? This line? Oh, okay. So remember that before doing this, we had only M1 and M2. M1 for the angle of the pendulum, M2 was the for angular velocity of the pendulum, right? Okay. Now I want to add another simulation, the same system, I just want to plot the nonlinear differential equation of that. So I need M3 as the new angle of the nonlinear differential equation and M4 as the new angular velocity of the nonlinear pendulum. See what I'm saying? So I need two more state variables for that. See what I'm saying? See? 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 I modeled this previously. Okay? How many state variables it has? Two. Remember? M1 and M2. Now I model this, a new system, nonlinear. I need to add more two state variables, right? Here was M1 and M2. The next one gonna be M3 and M4. If I add another system, I'm gonna do that. Next one gonna be, you tell me. M, yes. If I add another system, second order gonna be 7 and 8. See what I'm saying? MATLAB has a logic. It's like a human brain, okay? I define new state variable for our new system. So this is for, I'm writing here for your reference when I'm sharing. M1 and M2 are state variable of linear ODE, okay? ODE of pendulum, pend, but M3 and 4, okay? I'm just writing here, okay? M3 and M4 are state variables of nonlinear ODE of the pendulum. Clear now? Oh, what the hell is this? Okay. Clear now? Okay. So now, but now I want to plot the inverted pendulum also here. So what I'm gonna do, sir? I'm add another two state variable, right? I'm gonna say 6. So remember, oops, remember, I'm gonna stick to a nonlinear version of that. First of all, this must be 5, 6, 6, 5. And we don't have natural frequency for that. And here is positive. All of you go look at your notes. Guys, I'm just reading what you have in notes. For the inverted pendulum, the differential equation was this. G over L sine of theta was 0. And remember, this one had a pair of pure imaginary roots, but here we had S1 and S2 was a pair of real roots, one of them located at the right hand side of imaginary axis. That this makes your system unstable. Remember I taught you? Yes? Huh? So here you have G, because we divide by L, okay? G divided by L, and here is positive, see? In these two, they are negative, see? I told you, when you look at the signs of differential equation, it speaks with you, okay? So, now I have to add 2 more initial condition. Okay, let's do that. I'm saying, starting from, I don't know, pi over 4. Starting from this angle. Okay? Pi over 4 and 0. So, you're going to have 2 more. Pi over 4 and 0. Now you have 6 state variables. These 2 for the linear pendulum. These 2 for nonlinear pendulum. These 2 for inverted pendulum and nonlinear. Clear, guys? So, now I have to add this here. Here we go. But this counter gonna be angle gonna be which of them? 1, 2, 3, 4, 5. The angle is 5, M5. So here you're gonna say M5, M5. Okay, but we have a difference here. For this, okay, its x is the same. Okay, but its y, gonna be different. See, I'm writing here, guys. X of this is the same as this. XC gonna be L sine theta, R cosine gamma. But y of this gonna be L cosine theta, positive, because it's above it. L cosine theta plus R sine theta, or gamma. Because this is above the that unit. See? Here we go. Clear, guys? Yes? Yes, everybody? The y of the circle is this. So, what I'm gonna do, just for reference, okay? I'm generate this. I'm getting that 3. So this is gonna be 5. Okay, 5. And y of this gonna be positive. Okay, here was negative for pendulum. So this is for particle of inverted pendulum. Understand, everybody? So we plotted this. I'm gonna put as green. Okay, green. And now I have to hold on about the circle of that. So circle of that, hold on. You see, I put hold off at the end of that everything. Here is hold on. But here, when I'm done, it's gonna be hold off. So you're gonna have circle of the inverted pendulum. I'm making green to homogenize with that. Okay, here we go. But I have to change this to 12 also probably. I'm gonna make it to 12. First, let's debug it. Oh, something is wrong. What's wrong? Oh, this is, oh, see? There we go, guys. That's wrong. I forgot to fix it. Here's positive, see? Positive for the inverted pendulum. So if I do that and run it, what happens? Oh, okay, sorry. Here we go. As I promised you, it is unstable and the angle increasing. See? Woo! Angle increasing like that. See? See? Going upper even this time. Okay? Simulation continues, eventually gonna be like this. See? Going higher. Next time we're gonna be going normal. So this is nonlinear, I mean that unstable inverted pendulum based on the math that we do. Here we go. Um, oh, but let me double check a thing, guys. What is this? Okay. So, here? Oh yeah, I see that now. I was checking that. Thank you. Because I have to double check because I'm developing with you guys. Now I wanna just make a comment. Oh, okay, you know how to make a comment, that's right. Pushing Control and R, making your things comment. Okay. Now I'm gonna make a simulation to 30 seconds, and I wanna plot the angle of the inverted pendulum. Okay, and this is figure number 3. I'm saying is number 4, and I want to say it's 5 just to see. Okay, okay, yeah, okay, looks fine. Now guys, this is what I want to teach you. Guys, I'm commenting this out. Control and T. I'm sorry, R. Now I want to make this interesting for you guys. And Control T makes uncomment for you guys. Guys, look at here, all of you. This was nonlinear differential equation of pendulum. Also, we linearized this to get these roots, that's right. We removed sign, remember? Okay. Now, if I plot the linearized version of that, guys, look at here. I'm saying I'm removing this sign. See how different it can be after linearization. It's very interesting, guys. Look at here. Now I linearized. Okay. I'm in inverted pendulum. Oops. Now you see the difference? Yes? Yes, guys? Everyone?
Yes.
Because in the original nonlinear, still you have a harmonic term. That's why it's going a large angle, coming a large angle, coming a large angle, coming back. It's unstable, but it's like this. See what I'm saying? Well, when you linearize, we got this in the course. We got this kind of behavior. Angle increasing forever. You see, when you linearized, okay, and unstable, oh my God. See now? That's the difference between linearization and for the inverted pendulum. So make sure whatever that you are doing, linearization is not good at any point. See, such a crazy movement after linearization. Okay, for the pendulum, which is a marginally stable system, originally is based on the differential equation, linearization works, but a little difference works. But for the inverted pendulum, which originally, because of this negative sign, it says your system is nonlinear, it's going to be a huge difference. Clear, everybody? Okay, now I want to extend this because here, because I'm going to finish it, then next week next class I'm going to do Laplace. Here you had the support area, guys. I'm saying is this triangle. I'm saying rectangle, okay? So to make it interesting, I'm putting this here. So I have to plot this. I have to plot this and put on the top of the pendulums. So what I'm gonna do, I'm gonna put here is 0 and 0. Okay. Here gonna be this point. Gonna be -1 and 1. This point gonna be 1, -1 and -1. 1 and -1. This point gonna be 1 and 1. This point gonna be -1 and 1. What I'm gonna do, I'm gonna go counterclockwise. I'm gonna rotate and use the fill command. Fill, as I did. Look at here, guys. I'm saying, hold on, fill. This is the command, guys. The first x was -1. Second x was 1. Third was 1. Fourth was -1. Here we go. These are the x. Look at here, guys. -1, 1, 1, -1. So y's are -1, -1, 1, 1. Look at here. And now y's. Y's are minus 1 correspondingly. 1, 1. Here we go. I'm saying with put it with color of black. Black in MATLAB is K. Let's see how it looks like. Oh, there's a typo here. Here we go. That works. So if I do that, hopefully it works. Too much argument. Minus 1. No, I think I have to do this. X of cube y of f of rectangle rec y of rectangle. Here we go. Putting outside of that. So here gonna x of rec y of rec. Okay. Hopefully it works. You know what, guys? I have done this 10 years ago. Okay, so I am trying here color. Oh, oh my God. Yeah, you're right, man. I'm getting older. Here we go. Now we have the support area. Okay, but the point is that, guys, you have to put this x and y in sequence, clockwise, or if you start from here, I'm sorry, counterclockwise, or we start from here, clockwise. You start from here, clockwise. See what I'm saying? Or starting from here, counterclockwise. You cannot do this and this and then and this and this because it's gonna plot you a stupid thing. See what I'm saying? Yes? Yes, guys? So now you can add a text here. Say, hold on, text. Okay, what's text? You have to give a coordinate to the text. I don't know. It's A6 and 10. Then you can say theta for pend and invert pend, for example. Okay, and it's a text that you can read. Let me pause it, and I'm done with the coding for now. Oh. So what's that? Oh, I'm doing here, guys. What's wrong? Oh, okay. What's going on? I did a mistake. Something. Oh, okay. There we go. See, we can type it here and make a movie. Actually, I have to shift it here to 0 like that. Okay. Say it to 0. Well, obviously, you can say line width, I mean font size of 14 to make it more clear. Okay, there we go. Okay, you can do too many things. So, but the take-home message is the difference between the linear and nonlinear differential equation, guys. Understood? Yes, everybody? So linearization for the unstable system originally it's a joke. Okay, as you see here. Okay, don't do that. Linearization works on the equilibrium point. And okay, guys, give me the answer of this. Why I cannot linearize unstable system? Think about this and let me know the answer. Why I cannot linearize, as I showed you in the mathematical modeling, unstable system? Why? How we linearize a stable system? You tell me that. Around what? Around which point? Okay. So I'm saying unstable system. Unstable has equilibrium point. See what I'm saying? It's unstable. Okay? By itself. It cannot even stay at the position. See what I'm saying? Okay? That's why it's ridiculous. Okay, guys, so I'm gonna share the whole code with you, and you can even after graduation, even going to grad school, if you go industry, you can use this code. Okay, for extending whatever that you want to do. Yeah, here, here. Yeah, because in the nonlinear version, it has no analytical solution, but we linearize to get the solution. Okay, but you see, when it comes to simulation, reality, that sucks. This only gives us, okay, we have a pole in the right hand rule of the right hand side of the in the complex plane. It's a good proof. But even without going there, you see that this negative sign, as I'm going to teach you eventually, shows that your system is unstable. It shows that your system has a right hand side pole or root. You don't need to linearize it. You see my point? Okay. So you see the difference between them actually. So that's the joke. So, and even that I start from 0 and 0 for the inverted pendulum, it was equilibrium point. That's right. Remember 0 and 0, right? 0 and 0. See, 0 and 0 was the equilibrium point of the inverted pendulum. Look at your notes. If I run it, okay, what happens? What happens? Yes, because exactly I did it around the equilibrium point linearization, okay? If I increase to 6 degree, means in radian, okay? Now let's see what happens. Because remember, I told you the angle between 0 and 6 is the range that you can linearize, right? Okay. Let's see what happens. So that solution that we got, Joseph, okay, was for around the equilibrium point, but this that we got, okay, this solution was around the equilibrium point of the 0. See what I'm saying? But huh? Yeah. The equilibrium point of this was 0. Remember that you have in your notes. Around the equilibrium point of 0, we linearize it. But when you're out of the equilibrium point, there is no linearization, man. So I change to 6 degree. See again, it's gonna be unstable. At the equilibrium point, it stays there. See? Okay. See, this is the equilibrium point, exactly that we got. 0 and 0. Well, even I want to change it to 1 degree. Just slightly different from equilibrium point. Okay. Okay. Just 1 degree. What happens, guys? Why is it not moving? Interesting, right? Because of this. See? It takes time, slowly comes down. See? Yes? And it goes continue forever. Around the equilibrium point of 0? I'm going to increase the time to 0.5 to make the simulation more. Okay. This is 0. Equilibrium point of the 0. It stays there, right? Okay. But when you deflect from the equilibrium point of that we got 0, it's gonna becomes unstable. Okay. Now and I'm done with this. Let me finish this and you can leave and I'm gonna share the code with you. Okay. Let me change it to now original version. Sine of nonlinear. This. Because there's no initial condition, it's gonna remain there. Like what? Like these guys. Now look at this, very interesting, guys. Look at this, guys. I'm starting from equilibrium point of all of them. Here we go. All of them from equilibrium point. Pendulum, inverted pendulum. Linear, non-linear. Interesting, right? That's the equilibrium point of the system. It's in the rest. But if I deflect this even 1 degree, it's gonna be unstable. See what I'm saying? Yes, guys? No, no, that's a huge mistake, man. That's good for sharing. A current point does not make system stable. System remains there. Okay? But if I just deflect a little, I showed you 1 degree, your system by itself is unstable. See? Minus. Okay? It's gonna. Yes. Okay? Look at here, guys. If I just. What happened? Okay. If I just slightly deflect from the equilibrium point, just slightly, this is what you get. See? 1 degree. I kept the other one in equilibrium point. Here we go. Your system is unstable and it shows it's unstable. But which I change it to sine, the original version, guys. Okay? To nonlinear. So it backs. Because I change it to this. Look at here, guys. To sine, to nonlinear version of the inverted pendulum. So if your system is at the equilibrium point, it stays there. But if you deflect from the equilibrium point, if it is stable or marginally stable, it's gonna oscillate forever. If it is unstable, it's gonna be unstable. See what I'm saying, everyone? Yes? Okay, done. Any questions you may have? No?